The following program is brought to you by Caltech.
At this point, it's my pleasure to introduce Mike Stefanko, who had received his Bachelor of Science from Caltech in 1970 and is the chair of this year's Seminar Day Committee. Without his hard work and the work of his 18 fellow alums, this event would not happen. And it's my pleasure to introduce him and to thank him for his efforts. Thank you.
Well, as the General Chair of Seminar Day 2012, I extend the welcome of the Seminar Day Committee to all of you, and I give my thanks to our Meteorological Subcommittee. As you have noted, this is the 75th anniversary, and so the committee has decided we wanted to do something special. So we decided to have two exceptional general session speakers instead of just one. As some of you may be aware, a very interesting thing has happened along the way, and that is NASA postponed the launch of the latest SpaceX rocket from May 7th to May 19th. It was supposed to be launched about 10 hours or so ago. That means one of our speakers, Garrett Reisman, is in Florida and rather preoccupied at this point in time. In fact, because the launch wound up being aborted, he'll be preoccupied for the next few days. They're going to try again 3 days from now, is my understanding. However, in the Caltech tradition of resourcefulness, Garrett was on campus last Thursday, and he and I tracked down a video camcorder, and he recorded a few comments and provided us with a video. So in lieu of a full talk, we have a few moments that he has offered to share with us. So I'm going to ask the tech people to now roll the tape.
Hello, my name is Garrett Reisman, formerly of NASA and currently a project manager at SpaceX. And if you're watching this on video, it means unfortunately I couldn't be with you today, and I do apologize for not being able to be with you at Seminar Day. I was really looking forward to it. However, it also means I'm in Florida, just hopefully celebrating the successful launch of the third Falcon 9 rocket and the second Dragon spacecraft on a mission to the International Space Station. So it's hopefully a very exciting time for the entire space community, and I hope you're also able to enjoy that. So it's all really for the best, because actually I look a lot taller and more handsome on camera than I do in person, so maybe it's all for the best. But if I were with you, I would love to talk to you a little bit about what's happening right now in this new realm of commercial spaceflight. And to give you a little background, I joined up with NASA back in 1998, and I was an astronaut for 13 years. I flew 2 missions, but all on the space shuttle and all to the International Space Station. And I had a fantastic career and a fantastic flying career. But at the end of that second mission, I had a decision to make. And that decision was I could continue to stay with NASA and fly another mission to the space station, this time on a Russian Soyuz rocket. But at the same time, I was observing what was happening in this nascent field of commercial spaceflight. And in fact, while I was waiting for launching in my last mission on Space Shuttle Atlantis, we had an extra day where we had nothing to do because it rained in Florida and they were late getting Atlantis to the pad. And so we had a day of actually miraculous. So in that period of time, we said, well, let's go take a look at the SpaceX launch pad, because we knew they were about to launch the Falcon 9 rocket for the second time. And so it was an exciting time over there, and we wanted to see what was going on. And what we saw was really amazing to us. What we saw an incredibly streamlined and energetic and dynamic effort going on this launch pad. We could not believe the amount of people, for example, required to launch the rocket compared to what we were used to in our world at NASA. And we couldn't believe the motivation and the morale was so high. And we were astounded by all that. And in fact, it became a mantra for the rest of our training time and even during our mission. Whenever we were stymied by some process that was taking too long or something that just seemed ridiculous, we would say, well, what would SpaceX do? And so we saw that something interesting was happening there. And then after I came back from the mission, while I was still an astronaut, I was flying a T-38 jet to Edwards Air Force Base for some training. And when we landed that jet, it was the day that SpaceX launched that Falcon 9 rocket for the second time with the Dragon spacecraft. And this Dragon spacecraft orbited the Earth and was recovered that day, becoming the first private company to launch a spacecraft into orbit and return it safely to Earth. And that was a really a landmark achievement. And I remember when we landed at Edwards Air Force Base, the Air Force ground crew, one of the crewmen looked up at the tail of our jet where the NASA logo was painted, and they said, "Hey, congratulations on that awesome flight of the Dragon today. You guys must be so proud." And my first reaction was, well, actually that was SpaceX, so that was kind of not, I had nothing to do with that. But then I thought again and said, well, they did that in partnership with NASA, so why not? And I went ahead and I took all the credit. I said, thank you very much. Yeah, I did a lot of work on that, and it was all me. So, but anyway, the point was that this fellow was so excited, and that excitement I saw on his face was something, even as a space shuttle astronaut, I had not seen in quite a long time. So it really clued me into something was going on here. So I went and I did my homework, and I looked at what was happening in commercial spaceflight. I looked not only at SpaceX, but also companies like Sierra Nevada and what even some of the big companies were doing, getting with this new program like Boeing and ATK. So I knew that something serious was going on. And the more I looked into it, the more excited I got, and the more I realized that our future in space, especially in human spaceflight to low Earth orbit, is in the private sector. And I made a very difficult decision to voluntarily leave the astronaut program, which is not something you do lightly, because I'll be honest with you, being an astronaut was an awesome job. It was a great gig, and it had incredible fringe benefits. But I said, well, in 10 years from now, when I look back, do I just want to fly mission number 3 after flying missions 1 and 2? Or do I really want to have a chance to really alter the course of this whole industry? And so that's what ultimately led me to SpaceX. So with that, I will sign off and again say, have a wonderful seminar day. Again, my apologies for not being with you.
Liftoff. Liftoff of the Falcon 9.
As the former director of JPL and overseer of several current projects that you can read about on page 39 of your Caltech Connect, to keep this short, Ed Stone is well situated to discuss what we might be able to do with a little creativity in the area of unmanned space exploration. Please join me in welcoming Ed Stone.
Well, I'm really pleased to be here today. It's a 75th anniversary for the seminar day, but there are also other very important anniversaries which form part of my talk. So let me get logged on. So this is about exploring the solar system and beyond, because in fact we are looking beyond our own solar system, but we have many things we need to do here as well. And we'll just talk about a few of those today. This is the 50th anniversary of the first interplanetary spacecraft, the first spacecraft to reach another planet. 50 years ago this December, Mariner 2 flew by Venus and opened a whole new era of planetary exploration, which is still developing today. There are really 5 frontiers of space. There's the physical frontier, that is going place where something has never been before. The knowledge frontier, understanding what it is we are finding and discovering. The technology frontier, the tools, techniques we need to operate in space, including launch, which you just heard a wonderful story about. The applications frontier, making use of space to better life here on Earth. And the human frontier, that is the frontier of humans in space and how to improve their efficiency and capability in the conditions of space. Those are the 5 frontiers, and I'll talk about our expansion of at least the first 3 today as we explore the planets. And these are huge frontiers, so you have to focus not only in a talk, but in fact in what you decide to do, because you cannot, in fact, operate on all frontiers at all times. And so I'm going to pick the frontier of habitability, that is, getting to places where there's a possibility that it was or is habitable for life. Mars, obviously, is one of the primary opportunities. This is a topographic map of Mars showing that, in fact, there is a debate about whether there was once an ocean up here, where it was much lower than it is in the southern hemisphere. There are large canyons. This is the Grand Canyon on Mars, which is as wide as the whole continent of the United States. So we have been on the surface of Mars a number of times, as you can see, most recently with the Spirit and Opportunity rovers. And it's by going and landing that we're beginning now to ask the question, were there habitable conditions on Mars? Was it possible microbial life did evolve at one time? There is some evidence. Water here on Earth, wherever there's water, there's life. It doesn't matter whether the water is near freezing, whether it's near boiling in the bottom of the ocean, or whether it's deep underground in a well. Wherever there's water, microbial life seems to have evolved. And so look at these streaks which formed on the wall of the Newton crater. Certainly suggestive that there is water seeping out occasionally, periodically, onto the surface of Mars. But we certainly know from the large topographic features on Mars, there was a lot of water on Mars billions of years ago, but it's very dry today. The rovers are the way you explore. And the first rover on Mars was a little Sojourner. That was 1997. Then came the Spirit and Opportunity, which had more capability, and in fact did discover evidence again that there had been water on Mars. And now on its way to Mars, going to be landing on August 5th, just a couple months, less than 2 months from now, a much more capable rover, essentially a roving chemistry laboratory. On the large arm it has on front, in fact, let me back up and just point out to you that here's the arm. There's a large turret which can be placed up against rocks to drill in them and to analyze them. And then the main chemistry laboratory is basically back on the bus itself. And then there's the camera and a laser system up on the mast that you can see. And this is the turret that's on the arm. It has an instrument to X-ray shine X-rays on the rock to understand what the kind of rock it is. It has brushes and drills in order to sample the rock, and then deposit the rock into the chemistry laboratory, which is on the rover itself. Here's the rover at JPL. You can see these are 20-inch wheels, so it's a much larger small vehicle, basically. Weighs about 1 ton. And here it is, all tucked in with a descent stage on top of it. The red things are all removable items. These are the retro rockets to slow the entry down. But you can see it's all tucked up and packaged and fits inside of this structure right here. And this is the cruise stage, which then is currently carrying this to Mars. And when we get to Mars, this gets dumped away, and this then enters the atmosphere. Here is the descent stage. It's a two-stage system. There's an entry, descent structure here, and here's the rover beneath it. And as it approaches Mars, it will be winched down about 25 feet and lowered slowly down by this hover. It's sort of a sky crane. We had to do this because the airbag system that we developed for the other rovers could not handle such a heavy load. It just was not feasible to go with the airbag system. One needed a new system, and this is a new system. Landing is the hardest thing we do. And so it's always a challenge when you land, and that will certainly be the case. So what I'm going to take you on is there's 6 minutes of terror in the landing, as it's called, at the laboratory, for good reason. And that 6 minutes is going to be compressed into 45 seconds in this video. So here we go. As it enters the atmosphere at about 14,000 miles an hour, it just used aero braking. It just going into the atmosphere just like the shuttle does when it returned and so on. And then a parachute will open about 7 miles up. It drops down, and about 1 mile up, this is dropped out. The retro rockets fire, and about 66 feet up above the surface, once it's got itself the right way, it will start lowering the rover down, and then just slowly lower it down to the surface, the last 66 feet. And when the rover touches down, the switches on the wheels say landed, and it immediately cuts the cords because we don't want that to fall on top of the rover. That would not be good. So here's the rover. There's the camera system, and it has a laser, and so it can, and as well as do some. The laser fires into a rock, cause it to evaporate, and one can, with the camera up here, determine something about the chemical nature of the rock which was evaporated. And that is a way to look for interesting places, because when there's an interesting rock, we then can drill the rock and retrieve a sample from inside the rock, and then the arm will load that sample into the chemistry laboratory, which is inside the rover. You'll see the dust that was been drilled dropping into the container. And inside the rover, this particular station is an X-ray spectrometer, using X-rays just as in the laboratory here on Earth to determine what the crystalline nature of the matter is that's in that sample. So that's what this rover is, a much more capable rover. It has 10 times more mass in its instruments than the current rovers have on Mars. And the key thing is it can also look for carbon-based material as well, because we want to see if there was any evidence of the building blocks of life. This particular site is a large crater. It's about 90 miles across. It has a very large mound in its center, and the landing ellipse is, as you can see, is in the outer rim near, but down in the crater itself. This is a perspective view where you can see the mound of rock, and this is an area that was chosen because it has a lot of clay. We know from the orbiting spacecraft there are a lot of clays here. That means there was a lot of water at one time, and the layers, the strata of this mountain will be just like the Grand Canyon. It will be a record of the past geologic history and to try to understand what the circumstances are that could lead to a habitable environment in Mars, on this particular planet. This, I hope you can see it. This is that landing ellipse. This is the side of the mountain. And here are a couple of possible exploration trips up, layer by layer, stopping, looking at the rock, deciding which one's interesting, drilling it, analyzing it, and moving, if you like, later and later in time as the rover climbs up the side of this hill, this mountain. It's going to be an exciting journey, you can imagine, for the people who have to plan this, because this can't be planned ahead of time. We do not know in that detail exactly what the path is going to be, but we have some idea that one of these two might be feasible. But as usual, when you get there, and the rover itself will tell us basically the feasibility of the particular path that's chosen. So that site was chosen, I say, as a way to understand whether or not, or what the conditions might have been that could have created a habitable terrain. And the two key things is water and organic material. And so that's the kind of analysis that will be done, and will be done as a function of time as the rover climbs up the side of the mountain. Now, this is ultimately, this whole issue has to be, though, determined by bringing a sample back to Earth, because the challenge will be, we aren't going to bring back many samples from very many places, so we will use a mission like this to help our knowledge frontier, so we have a better idea of where we will go when we finally decide it's time to begin to collect samples. And this will be a stepwise process. It would be nice to sort of have one major activity which would result in a sample return, but I think more likely it's going to be a series of missions. Every 2 years one can go to Mars, and each year, every one of those, there will be a different activity which is leading to this eventual sample return. So what will be happening is, for instance, in 2018, there might be an orbiter, which will be a part of the communication network that's necessary, followed then by a lander, which would be like this rover, except it would actually cache. That is, it would take the sample, decide if it was interesting, and then permanently cache it in a way that protected it until a subsequent mission could go and retrieve it. And of course, the challenge will be doing that and then developing the ascent vehicle that you can store on Mars, waiting for the time when the samples have been collected out of the caches and loaded onto this return vehicle. So this is a long-term project, but it's one that can be done step by step, learning each time, both from the standpoint of the knowledge frontier as well as the technology frontier. But Mars is not the only place where there's water. It turns out there's a lot of water, we believe, inside of Jupiter. We don't know, and there's a mission I'll mention in a moment that will explore that. But even more interesting from a standpoint of habitability is this moon called Europa. This is Io. That's the one that has active volcanoes erupting on it. This is Europa, which is an ice-covered surface. Has no mountains and no valleys. It's the smoothest object in the solar system, and that's because it's an ice pack on a liquid water ocean. And the cracks you see here are developed as the tides from Jupiter nearby raise its surface up and down, just like our moon raises the surface of our ocean up and down, except this is the surface of ice. And it's that flexing of the ice which in fact melts the water beneath. And the cracks develop as that flexing occurs in Europa's orbit. Here is just a further demonstration from the Galileo mission, which orbited Jupiter and could get very close to Europa. And in fact, you can see these ice rafts, very much like what expected, where the surface cracked, the rafts broke away, and then the water would refreeze in between in these in materials. So in fact, it's now, I think, very clear there's a liquid water ocean. The question is, where are the cracks currently developing? Because we would like to find spots where we could get access to what's below, to see if in fact that's a habitable region, because it has the water, it undoubtedly has the organic material from all the meteorites that have hit the surface of Mars, of Europa over the years, and it has the energy, the chemical energy that comes from below. So I think the possibility is certainly it's habitable, but one has a challenge. And one of the key challenges the Europa presents is it's buried in an immense radiation environment. That's here on Earth we have the Van Allen radiation belts, the first major discovery of the space age. In Jupiter, the radiation belts are thousands of times more intense, and nothing can survive very long in that radiation. And any life would certainly be buried deep beneath the ice. But it makes it very difficult for a spacecraft as well. Here's Jupiter, there's Io's orbit, here's Europa's orbit, and I've just put Europa out here as a big black dot. It's actually, of course, quite small. And here is the design, innovative design, so that in fact one can take this long orbit, spending most of the time out here where it's radiation safe, and then diving in for a quick snapshot and back out. And doing this time after time after time, so that in fact one gets this sort of coverage of the site. That's Europa that you see below, and these are the ground paths of the spacecraft that would have these multiple flybys. Here, the red spots are where it gets to within 15 miles of the surface. Much of the time it's yellow, which is about 150 miles above the surface, where one can look to see where the hot spots are and do some remote sensing of the surface in preparation perhaps someday for actually returning and seeing if in fact this is a habitable place in the solar system. This is the kind of thing, what it looks like when you look at it from here's Europa, again, that's Jupiter in the background, and these are the way the flybys for this particular tour would look. Obviously, the details can be will change by the time such a program would happen, but hopefully something like this could get started this decade in the years ahead with this innovation about how to do it and to minimize the radiation effects. We have one mission on the way to Jupiter, which will sort of actually use this idea of diving in and coming back out, and that's a mission called Juno. It was launched last year. It will arrive July of 2016, and it will go into a polar orbit around Jupiter so as to measure the gravity field. We're trying to understand what is inside of Jupiter, how much water there is inside, and what the structure is inside as clues to how the solar system formed. And the challenge is, of course, the radiation environment. So what the plan is to put it into a polar orbit, but it's a very elongated polar orbit. It zooms in from north to south underneath the radiation belts and then zooms back out. This is what it looks like from the side. So here's an orbit which spends most of its time safely outside. It sweeps around the radiation belts, inside the radiation belts, and back out. And slowly but surely, as the time passes, the orbit precesses, and eventually radiation we will have to pass through the radiation. But by that time, we will have done the interior mapping of this giant planet and have measured how much water is in it. Not that we think there's a habitable zone in Jupiter itself, but because this will help us understand how these giant planets formed in the solar system, and the quantity of water there is key to that analysis. On to Saturn. There's also a couple possible, one possible habitable zone in Saturn, and another one that's interesting from the standpoint of life. So here's Saturn, as seen by the Cassini spacecraft, now in orbit has been since 2004, a huge storm system that you can see up in the north, and you can see the rings here basically on edge, and here are the shadows of the rings. The sunlight is blocked by this coming down this direction, so it casts the shadow on the surface. There's a particular moon, a small moon called Enceladus. This is the Voyager image of Enceladus from back in the early 80s. It's about 300 miles across. This is a little tiny world, but look at its surface. This is what we thought it would look like, an ancient surface heavily cratered by impacts. But look at this, earthquake faults, a surface that's very smooth. This has been kind of renewed by some geologic processes. It's the whitest, brightest thing in the solar system. That means, again, very fresh water ice on the surface. And it turns out it is in the center of a ring called the E ring. It creates a ring around Saturn. So that's what Voyager found. And then the Cassini spacecraft, when it got back to Saturn, realized there's something was happening. What happened? And it found it's happening now. There are geysers erupting from the south pole of Enceladus. This is an image. This is not a cartoon. This is what it really looks like. It's 300 miles across. Huge geysers erupting, water. Clearly, there's evidence that there's liquid water, and the challenge is this another habitable region for exploration? And it turns out those plumes are coming from these cracks. They're called tiger stripes, if you like, large faults where the plumes are erupting from something which is keeping, this moon is very cold, it's very cold at Saturn, so something is keeping the interior warm enough that the water can gush out into these plumes which show up. Now the challenge with, the technical challenge here is, again, it's going to be very hard to go into orbit around this little moon, so it may be that the right answer, again, is to do, as we're currently doing with Cassini, is to put something into orbit around Saturn, but have it fly by very closely, within tens of 20, 50 miles of the surface of this moon time after time, and sample the material coming out in those plumes to see if there's evidence of the building blocks of life, which would, of course, be part of creating a habitable zone. That's something which could well be done with a smaller scale mission than the Cassini mission, and it might be something that could be started later this decade, depending on whether it's competitive with other bright ideas. As I say, these frontiers are immense, choices have to be made, and this is going to be one of the choices that would have to be made. Now, there's another interesting moon at Saturn. It's not because it is likely to have life as we know it, but because it has the building blocks of life. That's Titan. This is about as large as the planet Mercury. If we were in orbit around the sun, we would be calling it a planet, but it's a moon. But unlike Mercury, this has a real atmosphere. You cannot see the surface of Titan in visible light because there's an organic haze in the atmosphere that's opaque. That haze is the smog on Titan. Here on Earth, we're used to smog, which is oxides, because we have oxygen in our atmosphere. This atmosphere is mainly nitrogen, like Earth, but no oxygen. Instead, it has methane, natural gas, and the effect of sunlight and other radiation is to convert that methane into more complex molecules, some of which polymerize and form these haze layers that we can't see through with visible light. Now, from the Voyager data, and it was predicted that there could well be methane rain on the surface. That is, because there was enough methane in the atmosphere, perhaps the water cycle on Titan is really a methane cycle. And so when the Cassini delivered the Huygens probe built by the European Space Agency, here, as it parachuted down to the surface, it certainly found what looked very much like dry stream beds. We know it's not water. It's much too cold. It's only 95 degrees above absolute zero. Almost surely liquid methane and perhaps ethane were at one time raining down in this particular area and presumably forming this flat sort of basin. Fortunately, the Cassini spacecraft has radar on it, and radar can see through those hazy layers, and indeed there are lakes. Lakes roughly as large as the Great Lakes. So these are not tiny mountain lakes. These are large lakes, almost surely of liquid methane and ethane and other stuff which is rained out, which has been made in the atmosphere and rained out. So the chemistry that's occurring there today in Titan's atmosphere may resemble, in some important ways, the chemistry that occurred in the Earth's atmosphere before life evolved, before there was oxygen, because our oxygen actually comes from microbes. So this has got to be a place that we're returning to, and again, the question is, what kind of system can we think of doing? A balloon-borne system that would float around would be one idea that's is being thinking about. Clearly, a rover with the right kind of chemistry laboratory to look at the molecular complexity and diversity on this body. These are the ideas, again, which will be part of the discussion in the years ahead in deciding what the next step is in exploring in the Saturn system. Now, it's not just our solar system. Today, there are many planetary systems. This is the Kepler mission, which was designed to look for planets around other stars. It looks for planets that, in fact, where you can see the planet passing or transiting across the star itself, very much like Venus will transit across the sun once in a while, and you can see you can see it. You can see the spot on the sun, if you like, or you can see the thing in front of the sun, I should say. So here's how the Jupiter would look if it were to transit the sun. This is the sun, so then scale. So you could see, well, it will cause the sunlight you record to drop about 1%, because it's about 1% of the area. And there's what an Earth transit would look like, an Earth-sized object. About 1/100th of a percent. 1 part in 10,000. So it's a very small dimming of light. And so what this mission does is it has 42 very sensitive charge-coupled devices staring at about 200,000 stars continuously, looking to see if there's a dip in the starlight as a planet passes by. Now, that happens only if the plane of the planets is in your line of sight. So that means that not every star that has planets. In fact, most we will not see this way at all. Only those where the plane of the planets is lined up with the telescope. So here's an example of the data. So here's the brightness. Boom. That's Jupiter. There's Earth. Oh, here's blown up. But I think, and so you clearly don't believe just one such dip. You have to see it orbit after orbit after orbit. Then you go use other ground-based telescopes. There's a lot of work to decide which of these things are real. It's pretty clear that's real. But these smaller things, the things which are due to Earth-sized planets, take a lot of care and attention to be sure that it's not just something happening like a solar flare on our sun. Our sun's luminosity certainly varies as well. So to date, they have found there are 2,326 of these things so far. Not all will be planets. They're in 300 planetary systems. 70 have been confirmed as real, and one of those is in what's called the habitable zone. But it's fairly big, and so may not be rocky, but at least it appears as though perhaps one of that set already is in the habitable zone around that particular star. So these are all they're indirect indications that these planets are there, very important, but in fact, if you really want to understand habitability, you need to be able to observe the planet itself. And that's a big challenge because it's right next to a star which is 1,000,000 times brighter. And so it's trying to see, like see a firefly next to a searchlight. It's just very challenging. So the challenge we have is how to develop the kind of observing technology so that we can do more than just see the starlight dim. We can actually see the light from the planet itself and begin, because if you can analyze the atmosphere, you can tell whether it's possible that life has evolved. As I said, here on Earth, life is what created and maintains our oxygen atmosphere. Methane is another indicator of a living organism, as one of the trace gases that will be looked for on Mars, because it will be rapidly destroyed on Mars if it's not replenished. So again, there are real opportunities here, and innovation has to go hand in hand with exploring these new frontiers. And I want to end with one last anniversary. This is my favorite mission. Voyager was launched 35 years ago this year, and it will, in a few years ahead, become the first interstellar spacecraft. It was launched on the Grand Tour. 1977 was the year, once every 176 years, where a single spacecraft could fly by Jupiter, Saturn, Uranus, and Neptune, on what's called the Grand Tour. Launched in 77, and Voyager 1 flew by Saturn in such a way it's headed northward out of the plane of the planets, and Voyager 2 is headed more or less southward at about 30-some degrees in both cases. Headed out. And what's out there? Well, the sun has a 1,000,000-mile-per-hour wind blowing radially outward from it in all directions, and that wind creates a huge bubble around the sun called the heliosphere. All stars have these bubbles. They're called astrospheres in general. Ours is called the heliosphere because of Helios. And that wind, which is blowing radially outward in all directions, is supersonic at 1,000,000 miles per hour. So it goes through a sonic boom, a sonic shock, and then turns and goes down the tail. So the wind should turn and go down the tail this way. And outside, we are in interstellar space surrounded by matter that has come from the explosion of other nearby stars. Well, these things really do exist. This is a Hubble image showing a star with a bow shock in front of it because there's a wind coming from this direction. So there's an invisible astrosphere here. We can't see it, but it's there, and there's another small one you might be able to see up here. So we're inside of one of these on our way out. How close are we? I can't tell you exactly because no spacecraft has ever been there before. I can tell you that Voyager 1 is now 11 billion miles from the Earth. It is still inside the bubble, but that 1,000,000-mile-per-hour solar wind has stopped. So we're in a stagnation layer, or zone, or region. Must be close to the boundary. I just can't tell you how close. It may be another few days. It could be another few years. But it's hard to imagine that it's not in the near future on the scale of a 35-year mission. And once we, as I say, once we cross the heliopause and enter interstellar space, we will be in material that has come from other stars than our own sun, and we'll be seeing cosmic rays that have come from other stars that cannot get inside our own bubble. Expanding the frontiers of space continues. Thank you.
Questions.
I'm sorry?
We're not going to have time for
Yeah.
questions. Well, I think both Garrett and Ed have definitely fulfilled the Be Inspired part of our theme. So once again, please join me in thanking them for their presentations. As you head to lunch, I remind you of Jean-Lou's assignment. Look for those students in green. And I want to leave you with 2 words that you can do some research on: oral histories. Thank you again. Enjoy the rest of seminar day.